First of all, I'm actually very happy to be here with you today on this sunny day. So it's actually perfect timing to talk about solar energy, namely, which is a way to make clean and cheap energy with fun science that we are doing here in Enschede at the University of Twente. So my name is Rebecca Saive, and I'm an assistant professor at the University of Twente. So when I think about light, I might think of something else than you normally think about. So for me, light is a fuel. So when you think of a fuel, you might rather think of, I go with my parents to the gas station and like fuel up our tank for the car. But for me, light is really the most amazing source of fuel. And the reason why I find this so amazing is because sunlight is abundant. So sunlight will, in the dimensions that we can think about, never run out. We have so much of it. In fact, if we look a little bit at the numbers, so globally, we would only have to convert 0.02% of the total sunlight that comes to Earth in order to power all our energy needs. And even for the Netherlands, which is like a rather small country and also not always that sunny, even there it is possible. And we would only have to convert a small percentage of the light that comes in here on us in the Netherlands in order to fulfill our energy needs. And the other cool thing about light is that light can be beamed, like literally. So you can get light in the area where you need it, although you have the energy source actually somewhere else. So an example is you have the sun up in the sky, and you can power, for example, a remote hut somewhere in the mountains or in the forest with your solar panels. And there are other fancy applications of using solar energy as well, not just for electricity, but maybe you have heard of these light sails, like these spaceships that are actually being propelled by sunlight hitting them. Or maybe some of you have seen on some people's desks these what they're called crux radiometers that start like rotating once light hits these little blades there. And so what I would like to talk to you today a little bit about are several different aspects of solar energy. So first of all, I would like to address the question, is solar energy expensive? And I will already tell you no, but we'll get into this in detail. Then the second topic, I would like to talk to you about how a solar cell actually works. So how is the light then converted into electricity? And at the very end, I would like to tell you a little bit about my life as a scientist or as a physicist or as a researcher and what we do and how our life looks like. So, well, are solar cells expensive? Well, not really. So here you can see on this picture, my house in Enschede, and you see I have solar panels on my roof. And of course, I love solar cells. I find them really cool. So of course I would want to have them on my roof. But really the reason why I bought them is because I can save money on electricity. And the way it works is that first you buy the solar panels, and then you don't have to pay for the electricity anymore that you generate yourself with the solar panels. So that means that I have some upfront cost to purchase my solar panels, but then over the course of the years, I save money by not having to pay for electricity. And in my particular case, it will take me around 6 years until I will have paid or gained back all the money that I invested for my solar panels. So that's basically my individual case, or the case that your parents would have if they wanted to have solar panels on their roof. But now also, if you look at this from a broader picture, here I'm showing you three fairly recent news articles of examples where, and I'm sorry, I'm from Germany and I lived in the US, so I have here mainly German and US news articles. But you can see that both in Germany as well as in the US, I translate this for you. So here in Germany, people are now, like a very big electricity utility company, EnBW, is now building the biggest solar power plant in Germany without using any subsidies. Yeah, they're doing this just because it makes commercial sense. And then a recent study also showed that overall it is now cheaper to build new solar plants than to operate already existing coal power plants. Yeah, and also here in the US, there was an example of a utility company that built a solar power plant because it made sense from an economics point of view, not because they want to protect the environment, but just because they wanted to save money. And now you might ask me, well, but my parents say, my grandparents say, My uncle told me that solar energy is extremely expensive and it doesn't make sense to install solar energy. So why am I now telling you that's not true, and why did they tell you it is so expensive? Where is this coming from? Why have you maybe heard a different story? It is not that they have been lying to you, and it's not that I have been lying to you. The answer is very simple. The answer is that over the past, or over the most recent years, the cost of the solar energy has been declining exponentially. So what that means is that if you look here at the average price of a solar power plant, so that's shown here on this y-axis, and we look at how this has developed over the past, in this case, 15 years approximately, you can see how we started off with a very high cost. Only in 2006, it was still very expensive. And since then, this cost has declining further and further and further and further. So if your family members or whoever tells you solar is very expensive, well, they might be right when it comes to how the situation looked 15 years ago. However, nowadays, the situation has changed, and solar energy is now in many areas of the world the cheapest way to generate electricity, and the costs are further declining, and therefore it will soon also be the cheapest way here in the Netherlands. And the reason why the cost is further and further declining is through research and innovations. And so that's what we are doing, is we're working on research on solar panels in order to improve them even further and make them even cheaper. And now I would like to talk to you a little bit about how a solar cell actually works. So a solar cell is made out of a semiconductor. There are three different types of materials. There are metals, there are semiconductors, and there are dielectrics or insulators, so materials that do not conduct electricity. I know this graph looks like very simple or not simple, very dry and probably not easily understandable. So I would like to explain to you a little bit more why a metal, for example, is conductive. So a metal, such as aluminum foil here, I'm pretty sure that all of you know that such a metal can conduct electricity. It's a conductive material. How does the metal do that? Well, inside the metal, there are a lot of electrons. So you can see them here. They're basically electrons in a bucket. And the metal is filled, with these electrons in this bucket. And now in a metal, these electrons are now allowed to move around at slightly higher energy than the other electrons. I'm comparing this here a little bit with crowd surfing. So what's happening is that the electrons that want to move around in the material, they will go to slightly higher potential energy, so slightly higher up, and then they can move around freely. And you can really imagine this as a crowd of people. And normally the crowd of people would not be able to move around at all because there are so many. But by crowd surfing, by just going one level up, you are now allowed to just move around freely and can actually make it from one spot to another. And that's how metals work. So now insulators are dielectric, which means, for example, material like glass is of course not conductive, right? So I'm pretty sure you have learned this. You cannot conduct a current through a material such as glass. And the way, or the reason why you can't do this is because, again, you have your electrons sitting here in this dielectric. Still, there's pretty much the same amount of electrons, but the problem is they cannot move around. You can imagine it as a crowd in a room with a very low ceiling. So the crowd is not able to lift up the electrons and have them crowd surfing because there's a ceiling blocking this. It's just not allowed. They cannot access a slightly higher energy state. We call this an energy gap. So there are no energy states allowed right here above these electrons where they're sitting, and that's why they're just not able to move around. And now there is this third class of material. It's called a semiconductor. So semiconductor, you can see, for example, what I have in my hand is this silicon wafer. And now a silicon wafer or a semiconductor material is very similar to an insulator. There are also electrons here confined in this room, or in this room with a very low ceiling. So the crowd surfing is not possible. However, the next floor is not very far away. So what can now happen is that when light comes in, light is a light contains energy, and these energy bundles that the light shoots are called photons. And now the electrons here that are sitting there in our room, what they can do, they can take on this energy, and because they have now this energy, they can jump up to the higher floor. And what we have now is an electron sitting here on our higher floor, which we call the conduction band in our energy diagram. And now this electron is free to move around. And on the other hand, we have here created in our crowd, now these two electrons that are next to this gap that we have created here can now also move a little bit. And now we call the absence of an electron here in this huge crowd, we call this a hole, or equivalent to a positive charge carrier. So we say that this is the valence band, and we now have a positive charge carrier here. And so now this principle is what a solar cell uses. So a solar cell, which looks like roughly like this, what would happen is that the sun shines in light, shines in these photons. These photons then get absorbed by the electron, making the electron jump on the higher floor, on the higher potential energy level, and creating now a negative and a positive charge carrier. And then what's happening next is that this negative and this positive charge carrier slide down to opposite sides of the solar cell. So what would happen in your solar panel on your roof is you would have the positive charges going in one direction and the negative charges going in the other direction. And then you can basically use your solar cell like you can use a battery. You have a plus and a minus pole, and then you can put your external load, for example, your LED or your refrigerator or your car or whatsoever. You can put this now on your solar cell and charge it up with the power that you get from the solar cell. And so now here this mechanism of why do now my electrons slide right and my holes slide left, why is this mechanism occurring in a solar cell? And so now this goes quite deep into the physics. My apologies if not everyone can follow this. We'll get back to a different level later, but I wanted to mention this briefly for those who are really interested in this topic so that you already have a little bit of an idea what's happening. So in a solar cell, we have something that's called a PN diode. What does that mean? So a p-doped material is a semiconductor material in which we have a lot of holes. So a lot of empty spots in our valence band. On the other hand, we can also have the opposite. We can have an n-doped material, an n-doped semiconductor. And in this n-doped semiconductor, we have a lot of electrons sitting that are freely allowed to move around. So somewhat like in a metal, yeah? So we have on one hand now these holes that can move around, and we have these electrons that can move around. And if I bring now two materials in contact that have on one hand holes and on the other hand electrons, what will happen is that at the boundary of these two materials, an electric field will occur. And now the electron and the hole, so the electron can just slide down this electric field and the hole can slide up the electric field. And then we have the separation of the hole and the electron, which then creates us at the end this battery with which we can then, for example, drive an LED or an electric car. Here we have, like in the roller coaster, the electrons are falling down this potential energy here. And well, again, so this is my last very difficult slide, yeah, for those who are really interested in the field. Namely, when you then have your solar cell, yeah, your actual solar cell in your hand, and you want to know how do I use it now in order to, for example, yeah, use my LED or power my electric car or power my home. What you need to know is how does it behave in terms of what voltage does it give you out and what current does it give you out. And this is shown here in this diagram. We have these so-called current voltage characteristics where you can see the current depending on the voltage. And then you can see the power that is generated by the solar cell as this blue curve here. And there is one point where we can get the maximum power out of a solar cell. We call this the maximum power point. And the efficiency of a solar cell is given now by the power that the solar cell can give out divided by the power of the sunlight that came in. And a solar cell is, for those who are a little bit into electronics, a solar cell is a diode with a light source that gives current and has then certain resistors in parallel and in series. But all of this is really only for those who are really interested in the field and might consider to like look into this a little bit deeper, or might even consider to like build something with solar cells to have a little bit of an idea what is actually happening in a solar cell and what are specific, more technical characteristics. I do have a significantly simpler energy diagram of an electron in a solar cell, which is now very similar to what you guys learned about the roller coaster. And so that works the following. So what's happening is that when the sun shines the light on the solar cell, what's happening is that the electron in the solar cell now catches this light. You can think about it as it catches this light to give it the kinetic energy to jump up. So now you can think about your in your roller coaster going from down to up. And now when this energy has now brought the electron to a higher energy level, now it will be at higher potential energy. And because of this energy that the electron has now caught, the solar cell can now act like a battery with a plus and a minus pole. And now this excited electron, we call it also excited because it was excited by the light that it absorbed. This excited electron can now be transported with a cable towards your load. So that could, for example, be your LED. And then your LED would send out light again. And because it sends out the light, the electron loses the energy and falls back into a lower potential energy level. And then it would be transported back into our solar cell and complete the electric circuit of the whole system. So that's about how a solar cell works. There are many different types of solar cells and applications for solar cells. So you can, for example, something you might have never seen, but solar cells can even be made such that they're flexible and they can have different colors. They can be red, green, blue, anything else. They can be here, such as in the left, that they have light coming in from both the front and the rear side. They can be integrated in cars, like these race cars here that every year they meet all in Australia and have the solar-powered racing car event. Actually, there are several Dutch universities that are usually really good at this race. University of Twente is also always one of the best teams doing this solar race car in Australia. And there is even a Dutch company that is called Lightyear that makes solar-powered cars, like real cars that have solar cells integrated in order to make the cars drive further. Yeah, and so at the very end, I also wanted to show you a little bit how life is like as a scientist or a physicist or researcher, whatever you like. And so just very, very briefly to give some of you an idea what we are actually doing. So in my research group, what we develop are two different things. On one hand, we develop what I call it now a little bit like magic surfaces that you could, for example, put on your house. And these magic surfaces would then take on all the light that comes on your house and then sends the light towards solar cells. That's one topic that we're working on. The other topic that we're working on is to put solar cells in like tiny little robots, in nanorobots that are the size of my hair or even smaller, and then make it so that I can use a laser light and then shine it on my nanorobot and make the nanorobot move around. So these are the two big topics that my research group is working on. And very often when we do this high-tech research, we are performing our research in clean rooms. So in laboratories where we have to like gown up and like put like an overall on and hairnet and so forth so that we don't emit any dirt from our clothes or from our skin. And then we have like very fancy instruments with which we perform our research. So I have here two pictures of myself. Like this one was 10 years ago when I was a PhD student at the University of Heidelberg in Germany. Or this one was 4 years ago when I was in the US doing research. And as you can see, research is also a very international endeavor, a very international job. So very often, if you decide to go into this, you will also have very exciting opportunities to like travel to other countries and meet people from all sorts of regions of the world. And the research that I am doing is all in the, let's say, sphere of physics. And the specific topics are photovoltaics, photonics, nanotechnology, and material science. So if you ever hear any of these terms, that's the type of research that you would also do if you wanted to work on solar cells. It's all very related. And as I already said, so research is really something that you do with different people. So this whole picture of the researcher or the scientist being by themselves in the lab doing something crazy where the lab almost blows up, that's a very, let's say, outdated picture. So normally what's happening is that if you want to now, for example, come to our university, to University of Twente, and start a bachelor research, then you would, for example, come to our lab and together with me or together with other already a little bit older students, you would work on a research project in the lab and have all the fun. And then the group leaders, such as me, so I'm the group leader of this group of young people here that you can see in these pictures, they then guide the students and the PhD students in the lab, helping them to make the right decisions with their research that they are doing. And so that's actually a very, very fun job, like both from, I mean, when I was a student, I thought it was a lot of fun to do this. And now that I'm the project leader or the group leader, I'm also having a lot of fun, like guiding all the students that are now doing the research in the lab, or also some students do research on their computer and they're calculating and simulating using their computer to do certain parts of the work. Yeah, and as the last thing I would like to say that, I mean, I'm of course a researcher, I'm a scientist, and I hope that many of you will decide to study physics or engineering or chemistry or anything like that, ideally at the University of Twente. But really, solar energy needs all of you. So all of you, whether you're interested in science or whether you're interested in social professions, in economy or anything else, we need everyone to join our green energy movement, and we need supporters with all different types of backgrounds. Yeah. So to give you a little bit of an example, for solar energy, it's actually really important that we figure out what do people want. So if I come up with what I think is the most amazing idea to make a new solar power plant, and then, you know, all my neighbors say, well, but I really don't want to have that in my backyard, then it's completely useless. That's why we are actually collaborating a lot with people who are more, who are like better at understanding what the society wants. So what, like, for example, my neighbors would be okay with having in their backyard. And so you can also do research on these types of topics, even if you might not be so interested in what the electron does in a solar cell.